Right, so we've set up. Thanks very much for joining us tonight in our May meeting. And tonight, Professor Iver Cairns from the University of Sydney will be talking to us about his CUAVA 1 CubeSat and some CUAVA projects, but Iver's been working on his centre for about the last 3 to 4 years, and he's going to be telling us a bit about some of the current projects that he's got operating there at the centre. So thanks very much for joining us tonight, Iver, to talk about the centre and the projects.
Okay, well, thank you very much, Wayne. It's nice to see people here for this talk. Anne's here, but she doesn't bear any negative responsibility for any part of it. So I'd like to tell you, as Wayne said, a little bit about CUAVA, which is the ARC training center for CubeSats, UAVs, and their applications, and about some of our first CubeSat, the CUAVA 1 CubeSat, very imaginatively named, and about some current projects. Sorry, just get things back. Okay. So let me tell you a little bit about CUAVA itself. So it's not just me, it's of course a large group of people, including Andrew Dempster, Eleanor Bruce, a number of others you might know, including Xiaofeng Wu. And overall, we have about 11 chief investigators in other words, named investigators at universities, and 12 partner investigators from various companies and government labs. And you can see down at the bottom here, the cast of institutions. So University of Sydney, UNSW, excuse me, Macquarie University should be here somewhere right down here at the bottom, because they used to be in CUAVA as the Australian Astronomical Observatory. And then part of that split and went to Macquarie. And so that's our group there. 4 private companies: Wave Communications, Arbor Carbon, Sabre Astronautics, which we obviously is rather famous at the moment, and HiVista, with HiVista and Arbor Carbon being interested in Earth observations, either via satellites or via UAVs, and interested in interpreting that remote sensing data for looking at forestry, agriculture, etc. We also have 3 government labs: the Bureau of Meteorology, interested in space weather in this particular case, and 2 divisions of the Defence Science and Technology Group, which hopefully you can see the logo for, both the Maritime Division based here in Sydney, and also the one which gets named rather often. It's at the moment, I think, called Intelligence, Surveillance and Space. And then one American university, Rochester Institute of Technology. And our focus is trying to develop or help develop a world-class Australian space industry in CubeSats, UAVs and their products. So it's not just the science or engineering that the boys and girls at CUAVA can get interested in. It's also the products and services that we hope to develop for the greater good. So let me I've used the word CubeSat quite a few times. So what does it mean? It really does mean that you build your satellite out of cubes, which are approximately 10 centimeters on a side. And if you want, so this would be a 1 unit or 1U CubeSat. And if you want to make a bigger one, you make it in, for instance, 2 cubes, put one on top of the other, or a 3U CubeSat. CUAVA 1, which we'll talk about, is a 3U CubeSat. Inspire 2, which we put into space as a collaboration between Sydney Uni, UNSW and ANU, was a 2-unit CubeSat. And then bigger ones, such as the ones we hope to build next, will be 6 units. And these are, as I said, 10 centimeter cubes on a side, less than about 1.3 kilograms per unit, above 200 kilometers to be in space proper. And you get real power from having a well-defined standard. It's just like with the mobile phones. where the great rise of them came about because everyone said we're going to have a certain number of standards for the voltages, for the characteristic size, for the communication protocols on the electronics boards, standardize things, and then people could innovate within boundaries and create something better that was easily sellable. And that's the same sort of idea with CubeSats, where you standardize the size, the characteristics, and then focus hopefully on the payloads. So we'll talk a little bit more about CUAVA. We put in a proposal to the Australian Research Council. It was awarded in mid-2017. The amount of money is about $4.5 million from the ARC and 1.2 million from the partners over 5 years. So, you know, a bit over $1 million a year on average, and which all of us look at and we say, oh, that's a lot of money. And it is, but it doesn't go very far when you have something like, 12, 14 students, 5 postdoctoral fellows, an engineer, a operations and research admin manager, and you want to put things into space or onto UAVs. That money unfortunately goes fairly quickly. But we do have these elements now, the 11 partners which I've mentioned, 5 postdoctoral fellows, 11 actually that number is out of date. It's 12 PhD students and 2 or 3 master's students right at the moment, plus a number of undergraduates. We expect to do 2 to 3 CubeSats over our 5-year lifetime and have 1 UAV. So here I prefer the term uncrewed aerial vehicle rather than unmanned. So 1 UAV and 1 aircraft campaign a year. So a total of 5 over our lifetime. And we're now in our 4th year. And so we've got just 1 and approximately a half years to go nominally. So what are we wanting to do? These are the qualitative goals, trying basically to train people, next generation of workers in high tech, advanced manufacturing, entrepreneurship. So not just going to work for somebody else necessarily, but instead thinking about building your own company or helping to build that company that you go into, and with a major focus on commercial applications, both in space and also for UAVs. I think everyone on this call is probably more excited about space, but that is a market that is about 1/3 of the size for UAVs. And then the market for aircraft is even bigger again. So so that's one reason for looking at UAVs as well. Another is the idea of using the same instruments or payloads in space and on a UAV, because with a UAV, you're less than or equal to about 1 kilometer above your object. So you're able to get very good spatial resolution, but only a narrow region that you look at. Whereas in space, you look at a large region, but with worse spatial resolution. So the idea to go exploring is that you might, let's say you're looking for iron ore or uranium or natural hazards of some sort, like a flooded area. You might do the large scale work from space with a satellite like a CubeSat, and then go down to a UAV when you want to get really detailed information. So training people, human capital is the first thing, developing new instruments, technology and products, addressing particular problems in Earth observations, communications, and GPS, or as I like to call it, GNS, so global navigation system of systems type approaches. In other words, trying to look at the position of objects and the timing of events very accurately using GPS style data and navigation using those same things. And hoping to or trying to develop a world-class Australian industry in CubeSats, UAVs and related products. So we've got plenty of themes and projects, 3 themes: systems, instruments and products, and 12 projects. And, you know, different people like different things, but you know, I like plasma thrusters particularly because I'm a plasma and space sort of person. Others like high-speed communications, so trying to get a gigabit per second from a CubeSat. Going beyond in this third project, the idea of, you know, just a CubeSat standard to really making CubeSat components plug and play. You know, you and I, we're all happy, you know, putting a USB into a computer and the computer going off and finding the relevant drivers to read the files and so on. That doesn't happen with CubeSat components at the moment, and yet that's one of the regimes that we need to move towards if we're going to make them widely usable. Images of all sorts, small ones, and I'll show you one where instead of using a huge American satellite like Landsat, which has characteristic dimensions about 2 meters on a side and weighs a couple of tons, we can get the same, we will be able to get the same, if not better, spatial resolution from a CubeSat, which is 30 centimeters tall by 10 centimeters by 10. So compact images, hyperspectral, that just means you have a lot of frequency or wavelength information, calibration, validation, other things, and then all of the products to do with applications of Earth observations data, like looking to see the health of coastal mangroves or salt marsh, so marine ecosystems, sort of area called blue carbon, which I'll come to in a little bit. We're looking at things that we're all familiar with, like the health of of an orchard or a forest or a set of fields that farmers might have. Or if you're a bit more exotic, trying to prospect for minerals. The two next ones are GPS related. One of them is reflectometry, where the idea, and I'll show you some bits about this later, you use the signals from the GPS satellites directly, yes, to give you your position, timing, etc., but also letting those signals come down, bounce off the Earth from maybe the sea, and then come back up to you. And with that reflectometry, you can get information on the surface that's reflecting. And if it's the sea or the ocean, you can get estimates of its height as a function of time, which allows you to see waves, for instance, both the direction and the height of the waves. And if any of you have been on a cruise ship or an oil rig, this is the sort of information you care about a lot. And certainly the operators of those care about. Another one is radio occultation, where you're using the GPS signal as it comes towards you, and you're looking at the time delays, and using the time delays, you're able to get information about the density of the ionosphere. Whether it's for instance, if it's a, so to speak, a strong or dense ionosphere, then it'll be good at reflecting higher frequency radio signals and using, for instance, the over-the-horizon radars that Australia uses to the north to survey entities that might be coming towards us. And radio occultation is just a way to get that information. Connections to space weather as well, which I personally regard as extremely important, but I won't talk about otherwise. Okay, so let's go a little bit on progress. We've got all the people involved. We've had lots of discussions with startups and other companies, some of which are bearing fruit, and I'll talk a little bit about later on. We have all of the PhD students and more that we're meant to have. We actually have 12 PhD students, despite the government only giving us money for 11. We've also got 3 master's students that we're getting, 2 of whom are getting scholarships, 3 interns, number of honors students, and more than 30 undergraduates who've worked so far on our programs. And, you know, here are the names which don't mean much in detail, except to see that, you know, these names have, you know, a number of origins. So it's not just, you know, people from any particular region of the Earth in particular. Got got a number of international students, actually only about 3 here because Yijun Huang recently became a permanent resident, so he switched from being international to being domestic. And an aspect that's really important is the diversity of the students. And we have, 5 female out of 14 postgraduates, so about 30%, a little bit more than 30%. It's obviously not where we want it to be, but really that's quite good for the current time. And we're overwhelmingly domestic, and that's really important too, because we want to be training, especially Australian students, because it's Australian funds. And so I'm really very pleased with both of these aspects. Happy to talk about it later. Now, that's probably not what you want to hear about. Probably what you want to hear about is satellites and gadgets in some sense. So let me tell you a little bit about CUAVA 1. Some of the people involved, Shuilian Bai, who's our training center engineer, Yung Ho Un and Jun Wen Chung. So Yung Ho is one of our postdocs, and Jun is one of our colleagues from UNSW who's just gone to a startup, and he's now only working 1 day a week for us. But he's somebody who was absolutely intrinsic to the success of Inspire 2, for instance. And then there's a whole bunch of others of us. So it's a 3-unit CubeSat, so you know what that means. Here is a cutaway of the various parts of the CubeSat. And it obviously looks complicated, but let's start at the base here. So you see the 3-unit frame. Quite literally, it's a frame, which you then put boards or PCBs or components inside. But you also have things on the outside. Those include the solar cells, which you can see some of here. And it's interesting to note that 2 of those solar cells come from an Australian provider, Aerowave Communications, one of our partners, and the rest come from overseas. So actually we're going to be demonstrating some Australian tech in space from the point of view of spacecraft components. Got a number of antennas and apertures. GPS antennas, this little gray guy here, the square, and then the apertures you can see here, those are for the imaging instrument ISTI, which I'll talk about in a moment. Magnetometer, various sun and earth pointing things for our attitude determination and control system, or ADCS, which is part of this big block here. We've got a electrical power supply, or EPS here, onboard computer, the radio, the antennas, which deploy. So those are basically the spacecraft components. And then this didn't translate very well here, but we have a GPS receiver here from UNSW. And then the bigger one here called ISTI. ISTI is obviously a mouthful. The I is for imaging, the S is for spectrometer. Sorry, the I is for imager, the S is for spectrometer, the T is for Toloman, or rather Toloboy, and then the final I is instrument. So it's 3 instruments in one, which I'll talk a very little bit more about. And then we have the rush payload, which, as we'll see in a moment, is focused on reconfigurable electronics, so FPGAs associated with energetic particles coming from the sun in space weather events, coming into the spacecraft, causing a single event upset or bit flip, leading to problems in the electronics. The system recognizes that and then reconfigures to be able to remove that error in the memory or the computer code. So it's quite an important payload. And then we have a little radiation counter and a power data bus. And the thing that's interesting there is that many of us here use data over power lines or connectors. And we're doing exactly the same in space for our instrument, which at one level is a rather simple innovation, but it's also one of the first times that this has been done. So that's what it looks like. Here's a little bit more about the various instruments, somewhat old terms. Here's just a cutaway. So rather than having it exploded out like this, here they're put in place, and you can see all the various parts here. I don't think we'll keep going, but the ISG instruments, a hyperspectral instrument, etc., GPS receiver, the radiation detector, and then RUSH, which is the reconfigurable electronics. Okay, so one thing you'll notice here is perhaps that this area here looks rather bare or empty. It is. That's because we were going to have a high-speed communications payload from one of our partners, and that partner unfortunately was not able to deliver. And so we had to chop it out of the manifest approximately 1 year ago. And actually that's when the RUSH payload came on. But at times I was trying to get other instruments to get on and ideally to pay us something for that privilege. But for CUAVA 1, that rideshare opportunity has gone. We've now built the spacecraft, and it's future ones that will be interested in giving rides to other groups for money in general. So let me come to that a bit later. Okay, this is actually the current situation. We've really gone over that. I think we'll just skip over it here. So this is what the beautiful satellite looks like. You can see, this is obviously before we put the outside panels mostly on. You can see all sorts of wires going everywhere. And, it looks a bit complicated, and it is a jigsaw puzzle, putting together these different instruments and PCBs together, connecting them, making sure that the sizing is right, that they don't push the frame out too much or cause the frame to go in too much, both of which are problems. But everything works, and we're happy with it, as we'll show you in a moment. So here's another view of it, still being put together. See, it's quite tightly constrained. In the 2 units you can see here, the 3rd unit is up above here and is mostly empty at that time it was taken. But you can see it's become prettier, it's become more organized, and that continues on. So here's a view of CUAVA 1, actually at the Advanced Instrumentation and Technology Center at the ANU. And my mischievous joke is, of course, that this is truly an Australian satellite, as you can tell. And I'll let you amuse yourself as to why I say that. Yes, as Anne said, it's upside down. Here's a little view of us at ANU just before we started doing the thermal vacuum testing for the CubeSat, being held by Shirley Ann here as like a little baby. And this is Yung Ho over here. So something like this, you've got to develop the software, you've got to test it extensively, and you usually start here with a flat sat test where you get your components, you connect them together, you start putting your software on it, and you assess how well it works. If it doesn't work, you go back and you either reconnect it properly or you find the problem in your software. And eventually, though, you iron out many of those problems, and you get some software that looks good. You might put components onto a test rig like this, which is testing the attitude, determination, and control system. Let's just see whether the movie works. And you can see the slow rotation of the spacecraft. It's obviously it's not perfect here because you can see that Shirley Ann's holding the camera as well and moving it. You can see that it's rotating pretty slowly, and that's one of the sorts of tests that one needs to do for the attitude, determination, and control system. The spacecraft components are in the middle here. They're not They're not, so there's a lot of extraneous stuff that's required. Let me just stop that. Software, look, for those who care, we're using a Linux-based operating system called CubeOS. It was started by an American company. The attractive aspect is that it's open source. And so the idea is that different groups around the world can develop different apps and services. In other words, the software for a given spacecraft subsystem or instrument. And then you can take, ideally, an app and a service from one person, another one from another person, etc., put it all together, and you streamline the development of your software substantially. And we've actually given a substantial amount of software to this, this open source system. And we're thinking of, we mean Shirley Ann and Young Ho and June, are thinking of developing that into a business with a company called, what's it called? I'm total mental blank, sorry. Marketplace, that's what it's called, Marketplace. Okay. So now one of the issues about building a satellite like this is actually getting it to be the right size. And the tolerance is incredibly small. It's 100 microns. It's the width of a human hair. And so what we have here on the upper left is a metal piece which has a known thickness. And we have the spacecraft sitting on a very flat surface. And what we unfortunately found is that often we'd be able to slide one of these underneath one of the rails, one of the vertical columns here, indicating that actually the spacecraft was not flush with the surface beneath. In other words, it was not properly perpendicular or parallel, as the case might be. It wasn't parallel with the surface. In other words, instead of a spacecraft being beautifully parallel, one of the faces was at an angle. So not parallel, but slightly at an angle. And sometimes they were not perpendicular. Here is an assessment of trying to make sure how perpendicular the system was. This one is looking pretty good, but it wasn't always the case. And so we actually had to develop a capability in-house rather than elsewhere of measuring positions of rails and how parallel and perpendicular the surfaces were of order 10 microns. So about 1/10 the width of a human hair, and often over distances which are 30 centimeters, so over the size of the spacecraft. And personally, I find this extremely frustrating. I'm more a theorist. And so this sort of detail I didn't like at all. But it turns out to be really important because one has to fit the spacecraft into the deployer. And I'll talk to that in a moment here. So let's just come here, the deployer. Here's a case very similar to what the CubeSat CUAVA 1 will get put into. And the idea is that you put it in and there's a spring at the far end. And when an astronaut or the ground station commands it, this little door will open, the spring at the other end will go ping, and the spacecraft will come happily moving out. And so you have to be able to move your CubeSat in and out of that smoothly. So like this. Here is a movie showing Shirley Ann doing that. See, nice and smooth. It works. That wasn't always the case. When we first, there's a reference here to a second set of vibration tests. About 8 months ago, we thought we were ready to deliver. We believed the spacecraft fitted because we had put the spacecraft into the fit check case and it seemed to be fine, but we had to use a bit of force to put it in. And we were told that that was all right. And then JAXA, the Japanese Space Agency, which looked at it and said, oh, we see scratches on your spacecraft. We think you're not the right size. And we then had to go back and retest it. And as Wayne said in the chat here, you know, tolerance inaccuracies, both on our spacecraft and in the deployer and in the fit check case, are problematic. And when we first got told that we weren't the right size, I didn't believe it actually, or at least I said, that may be true, but what's the chance of your fit check case being the wrong size? Because we'd been told that previously, when Shirley Ann did a satellite, that it was the wrong size. So we ended up having to do this very extensive set of measurements to work out what was the case. And we found out that actually we were over. In some places, our surfaces were not perfectly parallel, but only by about 200 microns. So at most, size of 2 human hairs. And that was enough to make a big difference. So accuracy really is important here. Now you might say, well, fine, you know, you make something beautifully the right size, everything looks good, you behave as if it's you know, a baby, something you care about a lot, you carry it around sensitively, you don't drop it on the ground, etc. And then you get told to take it to somewhere and do a vibration test. And what does a vibration test correspond to? I mean, on the left here, you see a circle with a black piece pushing out that connects to this table. And basically inside here, you have an engine that is going to push this whole table back and forth extremely fast at frequencies that go up from about 1/10 of a hertz or so to about 10 kilohertz. So moving up towards the upper edge of human hearing. And the speed at which it moves will correspond to a maximum acceleration above 10 Gs. And this is because during the launch, a satellite will get vibrated back and forth, and you want to make sure that your satellite will survive. And those wires that I showed you before, you know, these guys here, you might say, well, surely it doesn't matter. But when you take some wires like that and you move it back and forth at 10 Gs, it turns out that those wires can hit another surface and cut it. You can cut it like a knife. Shirley Ann and others have seen situations where the support structures here have been cut by bundles of wire during the launch or in a vibration test. So it actually becomes really important to tape your wires and make everything neat and securely affixed. But here's just some of the things: the spacecraft inside a jig or a case. It's about to be vibrated along in this axis. Here is for a sideways one, another one here. Of course, we needed to put CUAVA 1 on it somewhere so everyone could see that. And you care about the axes that you're working on. You can see here the solar cells all beautifully ready, covered with film, in this case on the outside. Here's another view of it instrumented up. So you've got little accelerometers here to see how fast it's being shaken. I've gone through that. And here we were about 10 days ago with the antennas unfurled, successfully gone through all its tests, and we are just waiting for the Australian Space Agency to hurry up, shall I put it that way, and give us the overseas payload certificate so we can launch it. We want to deliver to Japan this week. In fact, we have to. It has to get to Japan by the 17th or perhaps the 18th of May. Otherwise, they will scrub us. And in my opinion, this is entirely, we've been waiting for a while now for the agency. Having said that, I've had a very constructive and wonderful discussion with the agency head, and the individual people are great. They've just got a bad process to work through. So what else are we doing? we're not just satisfied with one satellite, we want a number of them, and we have a number of areas that we're working on. So one of them is a charge exchange thruster, near and dear to my heart. So you have a metal piece here, another metal piece here, cathode, anode, high voltage supply. And what you want to do is to accelerate ions outwards. And as they go, they might hit some gas molecules, an electron, or sorry, get very close to a gas molecule. An electron will jump across from the gas molecule onto the ion. It becomes a fast neutral, and that fast neutral happily leaves the spacecraft and moves out at, let's say, 100 kilometers a second if it's hydrogen. And then that release of particles out this way is a rate of, it gives you a change of momentum for the system. So got to conserve momentum, so the spacecraft gets pushed this way as everything gets ejected out this way. So does it work? Here is a picture that hopefully you can see. There's a nozzle for the thruster just here. Here's our plume of material leaving, of neutrals primarily leaving the thruster and then hitting onto a screen over here. Here's another couple of pictures. Characteristic size here, by the way, this is about 2 centimeters across. So these are small little devices. You've got something like 5 kilovolts or so operating between the front and back, and the pressures are very low, something like 10 to the minus 8 atmospheres or so. But you can see a very nice thruster plume coming out, and this is not a rocket burning engine, something like methane and oxygen. This is instead just the excited electrons in the neutrals, in the neutral particles here, re-emitting in H alpha, giving us the emission. And you might say, well, okay, that's fine. How much thrust is it? Here's an estimate or measurements calibrated of thrust versus the input power. And you can see this nice correlation. As you increase the power, the thrust goes up. And here's a plot of thrust versus power. And you can see, a nice, quite reasonable linear correlation. And we're getting, of order, half a micronewton here for this particular experiment at about a watt of power. So really quite reasonable. Truly, we want tens of micronewtons too, but this thruster has not been optimized. So that's one thing we're doing. We hope that to fly on our next CubeSat, CUAVA 2/3. We also hope to fly a GNSS or GPS reflectometry instrument. I mentioned some of the applications, so looking at the sea state, in other words, waves, for instance, you can also use it to look at floods, altimetry, soil moisture, multiple platforms, including CubeSats. And here's one of those instruments. This is the so-called Harry version 2 from UNSW, from Andrew Dempster and his colleagues, and from their collaborator CSKIP. And really, most of this is going to be uninteresting to people, but there are 2 GPS receivers in here, and then you have some processors as well. So you're needing to measure at 2 different frequencies, and this one's measuring at 2 different frequencies, so as to try and remove certain issues. So I think it's worthwhile just showing. This movie will go automatically. So one of the first things Andrew and his people wanted to do was to see whether they could detect objects passively. If you have a UAV or an airplane with one of these instruments flying along, and there's a ship on the ocean, and you've got GPS signals coming from space, hitting the sea, including the area by the ship, and then moving up, can you see a difference in the reflected signal associated with the ship rather than just waves? And so what this was showing was that when at this time here, you saw the peak flux here. And that was when you had a certain object, which was a ship about 100 meters long in the field of view. And I'm not going to go into any of the details here, but this is related to delay. And so this is the time information, and then this is the frequency information. But another version of Harry a little bit earlier. So more tech, which sort of looks neat, and then something which I think will come back to the Earth observations aspect and blue carbon. So some work that Chris Betters, one of our postdocs, and Sergio Leon Saval and me and Eleanor Bruce and others are doing. So we're looking at something like a 3U or possibly a 6U CubeSat. I've given him a certain allocation, about 5 by 10 by 20 centimeters. We want to try and get the best instrument we can on this. And so here's what we're looking at. We're looking at blue carbon. So things like looking here at mangroves, salt marsh, seagrass, that sort of thing. And the reason is because actually those blue carbon sites store 3 times as much carbon as a forest. So if we really want to make a big difference with regards to carbon capture, we actually need to do something involving blue carbon. So work on the ecosystems in that coastal intertidal region. And so that's one of our things. We want an instrument that's well suited to that. So that means it's got to be working towards the blue end of the spectrum, but we also want to be able to see the near infrared region. So this is a lot of details that you really don't probably care about, but we're going to have about a 4.5 centimeter aperture. We're looking towards a spatial resolution or ground sampling distance of 42 meters along the track, 10 meters almost across. And you say, okay, that's 42 meters, that's pretty big. 10 meters, that's big as well. You know, a decent sized whale might be 20 meters, for instance. So you really want to be down in the 10 meters thing. And then you say, well, you know, how good is this compared with other things? And it turns out that Landsat, which is, you know, a 2 meter by 2 meter by 2 meter satellite weighing a couple of tons, its spatial resolution is about 100 meters. So it's worse than we're going to do with a CubeSat, 30 centimeters tall, and with an aperture that's only about 5 centimeters. We're actually better than Sentinel as well, which is another commercial group out there, which only gets 10 to 60 meters, but not Planet, which is better spatially, but our spectral resolution is much, much better. We'll have something like a 15 nanometer band, and we'll have 34 across the, from the blue to the near infrared, whereas Planet has 4. So it's really showing the power of CubeSats here and what you can do if you design an instrument cleverly. And here's, for instance, Chris's instrument. Here we've got light coming in from the left. So through the aperture, secondary mirror, most of the light goes through here, reflects off the primary, comes down here, off to another mirror, comes out here, and then you put it onto a detector. And this is looking at it from the other direction, the YZ plane. Looks very beautiful, rather symmetric. But things look a bit more complicated. Here we've actually done another thing, which is here you have the light come in, bounce, and you might notice that we've got one detector here and another detector here. So what we wanted to do here was to have a really good camera. So people would be able to see, you know, visually by eye what we're looking at with something like 10 meter spatial resolution. And we'll couple that with our really good spectrograph and imaging spectrometer over here, which is able to disperse the light. So it's showing you the dispersion, so you can measure the wavelength information. So 3 different designs. You know, you can see that there's lots of choice here, lots of ways of trying to be clever. But we do it this way because with a panchromatic camera, well, you know what you see, and it's got very good spatial resolution, about 10 meters. And we can actually combine that with the imaging spectrograph or spectrometer to get 10-meter spatial resolution for everything. Whereas that's really rather difficult just with the spectrometer. You know, that's 10 by 40 meters in the other direction. So just showing some of the, the really clever optics we could do. And what I forgot to mention is these distances. This is 15 centimeters. This is 10 centimeters across here. And this one's 10 by 150 again. And if you go back to this design, this is roughly 5 centimeters. These are really tiny, extremely powerful instruments. Whereas, the ones that NASA flew, well, roughly 20 years ago, first on Landsat, are much bigger. So that's one thing. And then this is my last example, I think, another instrument from, this is our student Naif Al-Salem, and he's looking in the infrared because, of course, one of the areas of great interest to all of us is how much carbon we have around in the atmosphere, whether that's methane, CH4, or whether it's carbon dioxide. And we're looking at a system where we have a UAV at first. Light will come through the atmosphere, will bounce off something here and come back up to it. And we'll have the information both from the reflected path, and we'll also have the information, if we have a detection, the camera looking up, also the direct light to us. And we want to measure methane and CO2. We're all aware of how you get the yearly changes here in CO2, with the average, unfortunately, increasing monotonically over very long periods. This is some of the data that Al Gore saw many years ago as an intern, which got him interested in environmental science. And here we have the CH4, again, the yearly variations, but monotonically increasing. CH4, of course, is often associated with cows, for instance, one of the biggest sources, but others that are really important potentially are warming of the permafrost, both above the ground or in the ground, for instance, in Siberia, but also methane clathrates and so on under the water, especially in the Arctic and Antarctic regions. Methane's a much, excuse me, stronger greenhouse gas than even CO2 by about a factor of 10. So what are we going to do? Here's intensity versus wavelength. See all these beautiful spectral bands. We want to measure this guy here, this one here, and especially these two here for methane. Yeah, there's plenty of other ones in there that we could use, but we'll probably pick out a few and use them. We're looking at spectral resolution that's very good, about 0.5 nanometer, certain range in the infrared, and total mass of the instrument's about 1 kilogram. So it's too big and too heavy for our CubeSats at the moment. But here's one of the optical designs, the slit on the outside, which I'll show you the field lens for in a moment, collimator lenses, diffraction grading, focusing, and then the detectors here. And this detector here, unfortunately, costs about $30,000. And it's not one of the best ones. So we want to make sure that Naif flies this on a UAV, which is not above the water, so that even if it crashes, we will almost certainly be able to recover it. But okay, so here's the particular instrument details. And this is just looking at the field lens, another bit of the optics. What you're looking for is in the design is that these circles here correspond to the diffraction limit. So nothing can be better than that. and we're seeing most of our light nicely inside that circle. So we're very close to diffraction limited optics. So that's something that we hope will fly towards the end of this year on a UAV, and who knows, might go into a CubeSat of ours soon too. So my conclusions here, we're really working hard to try and help develop the Australian space sector, not just us, the academics, but also the industry part. We're really very heavily focused on industry here, but with research to be able to solve existing problems and future problems and have the human capital to do that. So not just solving last year's or problems, but looking at the future problems. So human capital, changing the capabilities of CubeSats, UAVs and their instruments, and progressing those devices to create value. Made a really good progress, excellent progress in the students and the research. CUAVA 1's ready for launch and waiting for the agency to hopefully give us a launch certificate. And as I said, it's frustrating there, but on the other hand, I know they're trying very hard to do what they have to do. And we've got many exciting developments for the CUAVA 2/3 CubeSat. Our thinking at the moment is that instead of having 2 3 units, we'll make 1 6-unit CubeSat with everything in it. We'll have multiple UAVs and ride shares. The instruments in CUAVA 2/3 will include the plasma thruster you just saw, the advanced hyperspectral imager, the GPS reflectometry instrument. It'll also have a plasma wave receiver that will be able to look at the ionosphere and study space weather. And we'll also have a student star tracker called CROSS, which is developed by a number of our undergraduates. So really very exciting, and we hope to be successful with the New South Wales government proposal to do a ride share for a 6-unit CubeSat for New South Wales government, in which we'll be having a competition for industry groups to put in payloads. And the best ones will get very severely reduced prices to ride into space. And we'll also have a commercial client part to that as well. So with our 6U, we'll be hoping for 4U to be cargo essentially, and to really help jumpstart New South Wales's move into the space sector. Hopefully there'll be announcements on that maybe this week, but in the next week or so at least. But really a very exciting time for us at CUAVA, for our partners, and I think for the New South Wales and Australian space sectors. Thank you.
Thanks very much, Iver. I think we've got some time for some questions, so we can put some up in the chat, I think. Now I've got probably something I was going to ask.
Right. Yes. You want me to? So one of them's, the first two are really from Wayne. So, with the inaccuracies, do you have to recheck it all after the vibration testing? And the answer is yes, we did that. So we had to, use our special little guide wheel, moving it along the rails, measuring to 10 microns, both before and after. And we found that the CubeSat did not expand or change its shape significantly during that, which we were very happy about. There's another question from Wayne about which group inside Sydney University designed the thruster, and that the answer is Joe Kashan and Richard Bowden-Reed and I, with some help from, or some inputs perhaps from Xiaofeng Wu, are the group that's done that work. We actually do have a couple of students now working on it as well. There's Dan Van Schendel, who's going to do simulations of that. So it's a very active, exciting time for that. So Lou, you mentioned competitors. I don't remember in which context I mentioned that, but maybe I'll give the following answer and then you can ask me to clarify it if you want. So competitors here can mean many things. We actually try to have a very constructive relationship with, not just obviously with our partners, but also with other groups in Australia and overseas. Now, yes, there are other groups trying to build advanced hyperspectral instruments and possibly GNS instruments, certainly plasma thrusters and other sorts of thrusters. And one of the difficulties is, of course, intellectual protections, so IP aspects, which do reduce the amount of discussion that we and they have. But fundamentally, I think we want to work together to make the New South Wales and Australian space scenes better for everybody. And so we might have a bit of competition while we're proposing, and then once somebody's selected, then the hope is that all of us work together to make it a success, with the idea being that a rising sea will float all the boats rather than, only one. And one aspect of that that's really crucial, I think, from a national point of view and a national sovereignty point of view, is that having one provider for anything is a problem. You want to always have multiple potential providers. You can't risk, from a national point of view, having bottlenecks that will prevent you from being able to do the things you need to. Okay, so a question from Wayne about, will a 6U CubeSat require a different deployment? The answer, I think, is yes and no. Yes, it's a different shape, so it needs to fit in a different box or launcher, but the basic idea is exactly the same. Again, it'll be a hatch that opens at one end and a spring that goes ping, as Monty Python would say, at the other end. Okay, so from Scott, have you looked at foil wrap protection for the circuitry, such as Captain tape and so on? So the answer is yes, actually. I believe, certainly for Inspire too, we wrapped all of the connections in Captain tape. And then we taped that to the, to something like the rails or PCBs on the inside. I believe that Shirley Ann has done that for this spacecraft as well. And kept on tape is wonderful stuff, as you know. It's you can get conducting versions and versions that are not conducting, reflecting versions and not versions that are not reflected. It's really useful stuff. So yeah, important to do. Okay, so a question from Alan. How are the satellites stabilized and how are they deorbited and what's the power generated? Okay, so how are they stabilized? We have an attitude determination and control system that has 3 coils in 3 perpendicular directions. So you can get, when you put currents through those, there'll be a relative force or torque due to the interaction of those currents with the magnetic field of Earth. So that's the primary way in which you stabilize things, by putting currents into the coils and putting torques on the spacecraft so as to stop it rotating and eventually have it oriented in one direction. There's also actually a reaction wheel for CUAVA 1, and that's because if we want it to fly along, sorry Anne, fly along like this, we want it to be able to go up and down like that, so as to look at a given object or not. And so we have a flywheel which changes the angular momentum in that direction, around that axis. So deorbiting at end of life. So we're going to go to the space station and be deployed from there. So we'll start at somewhere between 390 and 425 kilometers, depending on where the space station is when we get launched or deployed. And we'll drift down with time. It's just friction or collisions with air molecules and plasma particles that will slow down the spacecraft and heat it up. And as it slows, it will fall towards the Earth more, its orbit will become lower, and eventually it will get sufficient friction that it will heat up and start melting and eventually burning. So the spacecraft will die before it hits the ground. We predict, according to the calculations we've done, that it will be entirely burnt up and melted before it gets to 120 kilometers altitude. And that would take it somewhere between about a year and a half. It's difficult to be more precise because solar activity can give rise to heating of the atmosphere, and that puffs it up. And so you get more friction at a higher altitude, which brings you in faster. So if there's a lot of solar activity, we expect to deorbit quicker, and we are moving from solar minimum now into the rising phase of the solar cycle. So we're moving towards solar max. So that's one aspect. On the other hand, we have an ADCS. So we hope to mostly orbit like this as we're moving along, and that will reduce the cross-section, reduce the drag. But there will be times when we want to be like this, so as to observe particular things. So we don't have to do anything active there, but probably if we wanted to make it deorbit quickly, we'd let the spacecraft tumble, and that would increase the cross-section in general and get us to deorbit. The power generated, that varies obviously with whether you're in the sunlight and whether you're rotating or not, tumbling. We predict something like 1.7 watts averaged over the orbit. So we need to make sure that time averaged, our power usages are less than 1.7 watts. So that means many of our instruments have to be turned on and off. Okay. Okay, next question from John Lee. In CubeSats, are measures taken against radio frequency interference or electromagnetic pulse protection? So the answer is no efforts are taken against electromagnetic pulse protection. Basically, if an EMP goes off in orbit, we and most spacecraft are going to be dead. And many of us on Earth are probably going to be dead because one source of EMPs is nuclear devices. But radio frequency interference, yes, we have to make sure that we do not cause interference with stations on Earth. And so that means that we have to be, the ACMA requires us to be able to stop transmitting if we're interfering with others. So we have to work on that. But we're in the amateur, all of our frequencies are in the amateur band. We are going to work substantially with the amateur community, whether that's them detecting our radio beacons and putting them onto a website so we can get the data, or whether it's maybe over time us expanding the domain of the orbit in which we try and downlink data, users. At the moment, we're only going to downlink with and be controlled by the Mission Control Center / Responsive Space Operations Center down in Adelaide, which the agency has just opened and which our partner Sabre Astronautics is running. So we're expecting to work, well, Sabre will be working with us on that, and it's a great system that they've produced. Some of that with a little bit of help from us, but mostly internal Sabre work. Okay, Alan's got a question about the expected specific impulse of a plasma thruster. Look, I can't be precise there, Alan. I just forget the details, and for our particular one, the thrusts that we are getting are about what I showed there, about 0.3 to 3 micronewtons. Plasma thrusters like this are more efficient in general than certainly chemical thrusters and things like Hall thrusters, and the efficiency is a measure of the specific impulse, but I don't remember the numbers. So we'll have to come back to you on that. Scott has a question about what progress has been made to work towards CubeSat tech standards. And I think the answer there is probably not a lot that's public, or put another way, no one has yet released an agreed improved CubeSat standard. We do have a project along that direction. In fact, we have two. One of them's inside CUAVA, and we really haven't found a suitable student for that. And the other one is with SmartSat CRC, where we're working towards well, trying to understand the standards that we should have. So what would the current users and manufacturers like to have and think would be good? So that's work in progress. Oops, okay. Okay, lots of wonderful questions. Okay. So Lou, again, with all, can you put it down? Okay. Okay, with all the thousands of satellites being launched now and in the future, have you taken into account the possibility of collisions? So yes, the answer is yes. That is, for better or worse, part of the analysis we've had to do recently for the space agency. You know, we're launching only from 400 kilometers. Everything's going to burn up, but you know, there still is the possibility of the spacecraft disintegrating a little bit further up than the sort of 200 kilometers height that we expect if it's hit by something. And we've calculated the possibility of collisions, and from memory, the probability of a collision is about 1 in 10 to the 5. So about 1 in 100,000. As far as I'm aware, there's been no reported, believed case of a CubeSat being hit with debris and being able to report it. But it's also true that the number of spacecraft collisions with debris, you know, the number of reported cases is small. Doesn't mean they're not happening. It means probably that most commercial groups just do not report such data because they don't want their customers to, you know, believe that their capability is at risk. So they don't want to report bad news, but, you know, potentially bad news or bad things. Okay, but we have done it. Okay, so Julian, how do you maintain structural stiffness for the electro-optics components? And are you looking to evolve a 3D printable assembly for the optics? So okay, so let me answer the second part first. So almost all of the casing for the instrument ISTI and for other optical payloads that Chris Batters and Naif Al-Salem and others are developing in CUAVA are 3D printed. And that's really a good way to do things. You can get very, very good tolerances, and you can design it nicely in things like SolidWorks, and then build it, and then print it out, build it, and the system really works very well. So yeah, 3D printing is a great idea, and it's what we're using, and others are no doubt too. And how do you maintain structural stiffness? Well, I think that's just a matter of what components you're using and how you adhere them or attach them to things like the outer casing. So Chris Batters, for instance, uses SolidWorks to assess things like the resonant frequencies, the strength, the structural strength of the design, and so far there have been no issues with it, and yet we're using, you know, fairly much commercial off-the-shelf lenses. The diffraction grading is, I think, from Macquarie University, and it's, you know, it's not very special. You know, probably costs $100 or something in terms of components, maybe 1,000, but no more. So we haven't found that to be an issue. I think it's just taken care of in the design. But I agree, you do want to make sure that your components that you use, you know, are not going to fly out of the PCBs. If they're electronic components, they need to be properly mounted. You know, surface mounting is what we use most of the time. And then over the top, we'll often put a conformal coating of some sort. And in other cases, we'll use glue. You know, it's not super glue, but it's the standard things like araldite and so on, and they've got a proper name that's just right over flying away from me at the moment. But yeah, you definitely need to be careful of those things, but it's not too difficult so far. And as Julian says here, weight minimization, yes, yeah, both. I'll come back to Rick's question. Yeah, but good point. You want something to be strong, but flexible enough that when the vibrations come into it, as we go into orbit, that it doesn't shake apart. We don't want it to be too heavy. Don't want it to be too massive. Too large a volume. But you know, if it's too narrow, or too small a volume, or the weight's too small, you can have structural stiffness issues. So yeah, got to be careful with it. Okay, Rick, did you conduct any high altitude tests using stratospheric balloons? And the answer is no, we haven't. We actually do have a ride that we paid for with, but only quite inexpensive, with Robert Brand. And we did fly, before we flew Inspire 2, we did fly most of the instruments and so on from a stratospheric balloon down near Adelaide with a group with an Egyptian name that I'm forgetting at the moment. And so it has its place. We decided here that really the UAVs are probably the way we want to go. And even then, so far we haven't needed to do it. In part, that's because our original progress was, you know, we were intending to do our first CubeSat in the second year. And various things have prevented that from happening. And if once that happened, the plan was we'd do a UAV launch to test out the instruments. Then it would fly on the CubeSat the next time, and we do that sequentially, boom, boom, boom. And we've just had sufficient, issues with getting the CubeSat ready that we've pretty much done the UAV flights we've done in parallel, and with different instruments. And we haven't had quite as much of that test on a UAV, or for that matter on a balloon, than on a CubeSat approach. We haven't had the time to minimize the risk that way. But it's a good idea, and stratospheric balloons have their place, especially when you've got particular payloads you want to try out. So I don't disagree that it's a good idea in principle. Julian had a question about how's the ground segment organized, and so for that we have the partnership with Sabre. And so we're using their Piggy / Mission Control Center software. And we've developed, we being both of us, but it's primarily Sabre branded, have developed, or have managed to link Sabre's Piggy to software that can control ground stations and bring the data back and forth, and then put that over the net into both the Mission Control Center and also into data centers for us to be able to look at and use. So that's one part of it. It's a Sabre development, and it's branded under Piggy at the moment. And then with the ground segment, we're intending to use a station which is at the moment at UNSW, to do most of the actual communications back and forth with the spacecraft. But the Sabre system allows us to basically use any ground station that we have access to. So it's really very powerful. It's all internet driven. So you essentially click on a ground station icon, and the system will happily go off, connect to it, link in the appropriate drivers, move it to the right direction to start the pass, send the initial contact signal. We get the signal back. It'll go back to the controller. He or she will then, go through the segment. And much of that will probably be automated, but there will be opportunities for the controller to look at what's coming in, look at the battery voltage. Is it up near 8 volts where we expect it, or is it down near 6.5 where the spacecraft's about to go dead? What are the charging currents? What's the temperature? Does it look like the communications link has a lot of dropouts? So he or she can look at that, and there will be certain things that they can do if they see a problem. There can be communication with the flight controller and the CUAVA engineer, for instance, and decide what to do, whether it's, put the spacecraft into safe mode right now, or to wait and see, or, somewhere in between. So it's really quite we've really worked on quite an advanced system, and Sabre is going to be developing that further and using it, and we will be part of that, helping as well. And we will be, assuming everything goes well, CUAVA 1 will be the first Australian satellite to use that Mission Control Center and use that software, that the generalized extended Piggy sort of ground station, data center, control center system. So very exciting.
I think that's all the questions. Thanks very much, Iver. It's excellent talk.
Well, thank you.
Anybody else got any last minute questions?
Just one quick thing. It was Project Horus, Eva, you might remember, that did the balloon thing from South Australia.
Yes, well done, Tony. That's exactly right. Project Horus. And I should mention that Tony was part of the Project Horus trip, and he is also part of the team that is working. Well, it's the CUAVA Sabre team. He's a very important part of that, and has also helped greatly with the connections in with the ACMA, which has been great, just great.
Iver, can I ask a question out of total ignorance?
Yes.
What capacity or capabilities are evolving for satellites to be scanning topography for the mining sector, in terms of being how far can they see from such heights into the ground?
Look, I'm not a very good person to answer that, probably, but by analogy, I think it depends how you're wanting to do the scanning. So if you're using a radar system, like for instance the MARSIS instrument that Graziella Caporelli and others have been using, then by studying the radar returns at different frequencies, you can scan or less deep into the ground, and you can go, well, from memory, Graziella and colleagues were able to go of order 1 kilometre underground using the MARSIS radar. And that is an area that people want to use with radars. They're obviously interested in directly looking at other things like where ships are or aircraft or other things, but they could use that capability. I thought originally when you were giving the question that you'd be talking about laser scanning, for instance, and other methods of altimetry where you're looking at the height of the reflecting surface. So you can use lasers for that, as well as radio waves of various frequencies. GPS can be used that way as well, which is obviously a radio wave too, but in the microwave range.
Wouldn't you use lasers from a ground level? You wouldn't use them from satellites, surely?
I think it depends what you want to do.
Okay.
I mean, so the answer is yes. From the ground, you can shine a laser up on a satellite and get a reflection, and that will tell you where the satellite is. Now, yeah, so that's useful, but it's primarily telling you about the satellite rather than about your topography.
Okay.
So I think it depends what you're trying to do.
Thank you.
Yes, here's a question. Okay, Julian, can undergraduate students from other universities contribute? And the answer is certainly yes, in principle. We will be looking for some operators for our ground station, because after about 3 months, it'll turn over from being Sabre to being our people. And we haven't yet organized any of those people because we don't yet have the satellite, delivered. And so we didn't want to get them all organized and then have to wait. So yeah, potentially yes. And this rideshare mission that I mentioned, that I'm expecting to have announced, that involves University of Sydney, UNSW, and Macquarie and UTS. And we'll be expecting to get students from each of those institutions working with our payload teams and with the central project command. So yeah, potentially of interest, definitely, Julian. So Scott's got another question about gravimetric and magnetic instruments being used from aircraft, and could you put them in CubeSats? And the gravimetric one, that's certainly true. And there it's actually, I guess that's where it's a bit, the answer's a bit, it's related to Janine's question, that often what people have done is to get pairs of satellites, like in the GRACE 1 and GRACE 2 constellations, and they keep a precise knowledge of where the two of them are relative to each other. And then as they move over a denser region or a higher region, the gravitational pull changes, and so their orbit changes very slightly. And if you then study the, if they give their position as a function of time, their relative position, you can work out what is, why, well, you can work out how the gravitational acceleration is varying as a function of position above the Earth and of time. And you can do things like, well, look at changes in the mass distribution of Earth due to water, more water being in, particular lakes than other lakes, for instance. And ideally, people are interested in this from the point of view of searching for ore bodies or underground bunkers and things like this. So that's the gravimetric. Magnetic, I think the answer there is probably no. And the reason is perhaps similar to the gravimetric one. The magnetic field, it varies differently. For a dipole field, that falls off as 1 over distance cubed, whereas for a dipole magnetic field, it's 1 over distance square. Sorry, no, so let me get this right. It's the other way, yeah. Magnetic field, it goes like 1 over r cubed, whereas for gravitation, it's 1 over r squared. So the magnetic field intensity falls off more quickly with distance than that of the gravitational field. And so I think you'd find that you want your magnetic instruments pretty close to the ground. And so a UAV at 1 kilometer is going to have a signal which is 10 to the 4, 10,000 times bigger than a CubeSat at 100 kilometers. And of course, that satellite really wants to be at 400 kilometers. So that's another factor of 16. So I think realistically, magnetic instruments are not going to be very good for metal detection. They're really on the ground, or ore bodies. They're going to be really good for studying electromagnetic interactions between the Earth and the sun and the solar wind. So magnetospheric and ionospheric space weather. And that's why a lot of spacecraft actually fly them, is to look at those space weather effects. And I haven't said this about CUAVA 1, but that's one of the things that I also expect to be able to get, and that's the magnetic field data. See you, Ken and Al. Oh, sorry. Yeah. Sorry, wrong.
One more question. Sorry, everybody. Do you mind if I ask one more question?
Maybe one more.
Sorry. Okay. I'm moving to Port Macquarie, and I was hoping to do a microgrid of power, solar panel power network, but I was told the communication network for them to talk to each other is the problem. Do you see potential for little satellite constellations of these CubeSats to be able to resolve that problem so that we could have a good internet connection to be able to manage the power connection? Sorry, am I explaining myself well? No.
I think so, yes. I mean, the question's really about the so-called Internet of Things.
Yeah.
And communications back and forth. I guess I'd be surprised if, I don't think you can mean that the communications between the different solar panels in a small region would be an issue. I think you must be meaning over, kilometers.
Well, exactly. If you have a microgrid for a community, let's say the whole Port Macquarie, and so that it is resilient and independent. So Port Macquarie has its own solar panel inverters and networking, but every now and then it will probably have to kick in to the macro grid. So you need high-speed communications networks to be able to manage that interface, apparently.
Well, I mean, I think the answer is yes, that various people hope to be able to do things like that. We've got Fleet, for instance, doing the Internet of Things, Myriota as well, 2 Australian companies. And then you've got Elon Musk, you know, wanting his 10,000 satellite constellation, and it's focused on internet and communications in general. And so I think the answer must be yes, that in principle, that information could be available via satellite constellations rather than a local system over a sizable enough distance. But yeah, it's going to depend.
Yeah.
Okay, so Julian says, yep, about Skylink. Okay, excellent. And then Michael is wondering whether we can find large sunken metal ships and airplanes this way. And I think the answer, it may be possible with regards to the gravimetric analysis, but I think the magnetic one is probably, well, it could be problematic, just for the same reasons that I already gave, but also one more, and that is just that the ocean does conduct electricity, and so it will shield some of the magnetic signature. But quite possibly not all. Hey, it seems like we should let everyone go to bed. Well, maybe not bed, but go and have dinner or whatever else. But thank you very much for this opportunity to talk.
Excellent. Thanks, Iver.
Thank you very much for the opportunity.